A 5 kilogram box is pushed up a 30-degree frictionless ramp, starting from rest at the bottom, and to a final height of 16 meters by a constant applied force of 30 newtons that is parallel to the ramp. And we're going to start in part 1 by drawing the free body diagram. So we have the gravitational force going straight down. We have the applied force being directed up the ramp. And we have the normal force that is perpendicular to the ramp, and the ramp is frictionless, so those aren't any forces acting on it. And we know that the box is accelerating up the ramp. So I'm going to draw the separate arrow for the acceleration. In part 2, we want to calculate the acceleration of the box. So we're just going to start by redrawing the free body diagram with everything broken into components. So I'm going to rotate the axes, because with rotating the axes, only the FG will have to be broken into components. So we're going to have the FA still directed up the ramp, the FN still perpendicular to the ramp, the FG will break into an FG cosine theta across from the normal force, and an FG sine theta directed down the ramp. And then we still have the acceleration of the box going up the ramp. So let's do Newton's second law in the x direction. So Newton's second law, net force in the x direction is mass times acceleration. Let's look at what's going on in the x direction. That's the one circled in blue. That's going to be the positive force, which is the applied force, minus the negative force, which is the component of gravity, Fg sine theta, is equal to ma. And we can just rewrite this by changing the Fg to the m times g. Sine theta is equal to ma, and we want to divide everything by m since we're solving for the acceleration. So let's just plug in all the numbers. We have Fa, the applied force, is 30, minus m is 5 times g. So that's going to be 5 times 10 is 50, times the sine of the angle, which was 30 degrees. All that divided by the mass, which was 5. The sine of 30 is 1/2. 50 times 1/2 is 25. So you have 35 minus 25, which is 5, divided by 5, gives you the acceleration of 1 meter per second squared. Calculate the length of the ramp using trigonometry is the next part. So if we have this ramp, and we know the angle is 30 degrees, we know the height of the ramp, which was 16 meters, and we want to solve for the length, which is that side x over there. So from this angle, since this is a right angle over here, from this angle we know the opposite side and the hypotenuse, so you just want to use the trig function of sine of theta. So sine of 30 degrees is equal to opposite, which is 16, over the hypotenuse, which is x. So when you solve this for x, you get 16 over the sine of 30. That's 16 divided by 1/2, which is 32 meters. Calculate the speed of the box when it's halfway up the ramp. So we're just going to use some basic kinematics for this part and for the next part as well. So we know that the box started from rest at the bottom of the ramp. So VO is 0. The acceleration was the 1 from up here. The delta x, the distance the box moves, when it's halfway up the ramp, it's going to be half of this distance, so 16 meters. But in the next part, we want to find the speed at the top, so we're just going to end up in the same formula twice, one time using 16 meters and one time using 32 meters, and you're trying to find the final speed. And so when you pick the right kinematics equation, when you plug in the 16 meters, you should get the answer of 4 root 2 meters. And when you plug in the answer of 32 meters, you should get the answer of 8 meters per second. And that other unit should have also been meters per second. Okay, so that's it for the ramp part of the problem. Now we're going to move into the second part of the problem. This is projectile motion. The box has reached the top of the ramp right here, and is just going to be launched off in projectile motion. So the only thing that is common between when the box is on the ramp and when it goes into projectile motion is that the final velocity of the box at this point right here becomes the initial velocity for the projectile motion part of the problem. And that initial velocity, because velocity is a vector, includes both a magnitude and a direction. The magnitude being the 8 meters per second that we found down here. So the box is launched into projectile motion with an initial velocity of 8 meters per second, and the angle is going to match the angle of the ramp, so 30 degrees. So for the projectile motion part of the problem, which I'll squeeze down here, we know that the initial velocity is 8 meters per second at an angle of 30 degrees. Now with projectile motion, you always want to break things into components. So I'm going to start with the initial x component, the VOx, and the initial y component, the VOy. The x component, the formula for that one, was VO times the cosine of theta, and for the y component was VO times the sine of theta. So 8 times the cosine of 30. Cosine of 30 is root 3 over 2. So 8 times root 3 over 2 would give you 4 times root 3. And 8 times the sine of 30, which is 1/2, 8 times 1/2 just gives you a y velocity of 4. Both of these measured in meters per second. So to get in part 1, the maximum height above ground level the box reaches, if we go back up to this picture right here, you can see that the box is already 16 meters above ground level. It's just going to go a little bit extra to get up to that maximum height right there. So we just need to use what we know in the y direction, because y direction is what affects the height. So we've already got the initial y velocity as 4 meters per second. We know the final y velocity, when it reaches the highest point, is 0. We know the acceleration, because it's in free fall. Remember, this is free fall. It's not the acceleration that we found earlier right here. That was the acceleration while the box was on the ramp. Now the box is in free fall, so it has an acceleration of -10 meters per second squared. And we're trying to find the delta y. So with these 4 variables, the initial velocity, the final velocity, the acceleration, and the delta y, use the last kinematics equation, and if everything's done right, you should come up with a delta y that is equal to 0.8 meters. So the box goes 0.8 meters above the point where it was released. So if we look back at this diagram, we have 16 meters of height right here, and then the additional 0.8 meters right here, giving a total of 16.8 meters. Next part, calculate the speed of the box at the highest point. We've basically already done this because at the highest point, there is no vertical velocity. There is only horizontal velocity. And remember, in projectile motion, the horizontal velocity never changes. So the horizontal velocity we got right here, the initial horizontal velocity, that will be the velocity at the highest point. So you can just take that number for part 2, 4 root 3 meters per second. And finally, calculate the speed of the box just as it hits the ground. So if I draw let's continue the dotted line from the path. So as it's going along this path, when it hits the ground, it's moving in a direction that is part horizontal and part vertical. So we have to get both those parts, the horizontal and the vertical part, and then do the Pythagorean theorem to get the total velocity. We already know the horizontal part because we just said the horizontal part never changes. That's 4 times the square root of 3. And I will let you do some basic kinematics on this now to figure out what the vertical part is. But what you should find is that it's easiest if you take the highest point as your initial velocity. You could take the initial velocity right here with a block first left ramp, but if you take this highest point as your initial velocity, in the vertical direction, the initial velocity is 0. So by taking an initial velocity equal to 0 and a delta y of, now from the highest point to get down to the ground, it's got to go a total distance of 16.8 meters. And then we know the acceleration is 10 meters per second squared going downward. You could make it negative 10 if you want to, but if you do that, then you have to make the delta y negative because you're saying downwards the negative direction. And from that, you can figure out what is that final y velocity. That would tell you this arrow right here, and then you use the x velocity and the y velocity in the Pythagorean theorem to get the total velocity, which you should find you get an answer of 8 times the square root of 6 meters per second.